Okay, so here's where it all comes together. The reason we were finding these eigenvalues and eigenvectors is because they actually serve a pertinent part of the solution. And this is also where the linearity principle comes together, because the general solution of the system of linear ODEs, first of all, we require that the system has they have to be real eigenvalues, and they have to be two different ones. So in other words, lambda 1 can't equal lambda 2. They have to be distinct. And then the corresponding eigenvectors v1 and v2 respectively. Lambda 1 goes with v1, lambda 2 goes with v2. Then y of t, so that your x and y matrix, your solutions are k1 e to the lambda 1 t v1 plus k2 e to the lambda 2 v2, e to the lambda 2 t times v2. And this might seem a little cryptic as to why this works, and the proof isn't totally simple to come by, but I wanted to give you kind of a concept of what eigenvalues and eigenvectors were in this context, and the fact that things that seem somewhat independent actually help us find these general solutions. And then there's the linearity principle that if you have one solution, well, that would just be one solution, that would be another solution, and we would basically have two separate solutions added together would create one general solution. Now, what if they're the same? What if they're the same eigenvalues? Well, the problem with having the same eigenvalues is that means lambda 1 equals lambda 2, which means v1 equals v2, which means that these two terms just get added together to create one vector, and so they're no longer linearly independent. They're not linearly independent solutions because this vector is the same as this one, and as a result, you have a solution, but you can't necessarily you can only satisfy a particular subset of particular solutions, because I may not be able to, for example, satisfy I want x to the initial condition for x to be 2 and the initial condition for y to be 7. All right, well, let's put this together. It's pretty easy to put together once you have all the bits and pieces, and then we'll kind of talk about how to do this with the technology. Make it a little bit simpler on us. All right, so y of t basically is just another way of saying, and I kind of use this notation to make it look like it's a vector. So that means that my xy solutions are going to be k1 e to the lambda 1t. So I'm going to write k1 e to the lambda 1t, which lambda 1 is 2. And v1 is the vector 1, 1. So that must mean that I'm going to have e to the 2t times 1, and this one will be k1 e to the 2t times 1, and this guy will be plus k2 on both ends because it gets distributed, right? These are kind of two vectors here, plus k2 e to the lambda 2. Well, lambda 2 is 3, so that's 3t. And v2 is the vector that we chose to be 2, 1. And so now if you put this all together, you have the general solution that x of t is equal to k1 e to the 2t plus 2k2 e to the 3t. And no, we can't absorb the 2 and the k2 together because there's a k2 down here, and otherwise if you did that, then they would end up both being the same values, and they may not be the same values for the x and y solutions. They're for different purposes. And then here again I'll have k1 e to the 2t plus 1, or just 1k2 e to the 3t. And so now I can go back and solve for k1 and k2, and we could verify that if you plug this in, that these would in fact be solutions. And again, the cool part was that we were picking earlier on exponential functions because we know their derivative involves itself, and these are linear derivatives. So having exponential functions is necessary. And now in the theory that underlies this, it pops out. So we want to make sure that x of 0 and y of 0 are, we said earlier, much earlier, let's see, we wanted the initial condition to be that initially Bill's profit is 2 and Ted's profit is 1. So we want these to be satisfied. So in other words, we want 2 to equal k1 e to the 2 times 0 plus 2k2 e to the 3 times 0, and you know what's going to happen to these terms. And then 1 is equal to k1 e to the 2 times 0 plus k2 e to the 3 times 0. And so that gives us two linear equations. 2 is equal to k1 plus 2k2, and 1 is equal to k1 plus k2. Well, these are fairly easy to solve because you can solve the first equation for k1 and plug it into the second equation and solve for k2. But I'm going to give you a much simpler way to do this. And so let's rewrite these real quick. k1 plus 2k2 is equal to 2. And then we have 1k1 plus 1k2 is equal to 1. And what that boils down into is I'm going to convert this into a matrix form. And what I'm going to do in this matrix is this is called an augmented matrix. And we won't spend any time on developing this because it's kind of tedious. And really all we want is to solve for k1 and k2. So the augmented matrix looks like this. It stacks the coefficients, first of all, of the k1s. So my coefficients there are 1 and 1. Here for k2, my coefficients are 2 and 1. That's important that they line up. And then I'm going to basically draw a little dotted line here to indicate that that's the equal sign. And then on the other side, I'm going to list my constants as 2, 1. And what this will allow me to do is I can solve for k1 and k2, and I'll show you how. I'm going to pull up my TI-83. And what I'm going to do here is I'm going to go over to second and then the X inverse button and pull up my matrices. You may already have stuff in here with dimensions listed, but we're going to go over to edit and just pick matrix A. It doesn't really matter which one. And so this is a 2-row by 3-column matrix. So I'll press 2, enter, 3, enter. And now I'll enter these coefficients. So 1, 2, 2. And I don't need to do the dotted line to indicate that it's augmented. And then I'll just do 1, 1, 1. And now what I'm going to do is I'm going to actually run a function on this. And so I'm going to exit out of here first. So I'm going to go back into my matrix screen. But I'm going to go over to math first. And I'm going to find this function called rref, which stands for reduced row echelon form, which is what we're going to do here. So you want rref. You don't want just ref. We're going to pick that. And now we're going to dump in the matrix. So I'm going to go back to second matrix. Now take it from the names column because we just want to pull in the name of that matrix and close your parentheses. And this now shows up, it gives us the coefficient. So this matrix has been converted and manipulated so that it now has these 1s and 0s along the diagonal. So we'll read it off and talk about how to read it off in a second here. I'm just going to write it down first. So we have 1, 0, 0. I'm going to put that dotted line back there again. And then we have 0, 1, 1. And remember, these were the coefficients for k1 and k2. And this was the constant over here. So now if I reread these equations, I have 1k1 plus 0k2 equals 0, which basically just means k1 is equal to 0. That's not very interesting, is it? And then we have 0k1 plus 1k1 is equal to 1. And this implies that k1 is equal to 1. So as long as these are my choices for wait a minute, k2, excuse me. As long as these are my choices for k1 and k2, I now have a general solution for the system. So I'm going to plug these back in real quick so we can see what these look like. So k1 is 0 and k2 is 1. So basically my solutions for x of t is basically just 2e to the 3t. And my solution for y of t is equal to k2, which is, again, just 1. So I have e to the 3t. All right, well, let's just verify that this is what we would get in p-plane if we were to plot. Let's clear out these solutions real quick. And delete all those orbits. And I'm just going to pick the initial condition that we have here, which is 2, 1. I'm going to solve that. And it appears linear, right? But keep in mind that what we see when we compare x versus time and y versus time is going to be a little bit different. So there they are. And the blue line is Bill's profit function, and the red line is Ted's profit function. And in fact, Bill's increases much rapidly, right? Because his is higher here than, kind of zoom in on that little region there. So at any point, Bill's is always twice as much. Might be easier to see here. Twice as much as Ted's is. So they're both doing good, but one guy's got double what the other guy's got. And so that's our solution process. So don't worry about solving for these constants unless you like doing those by hand computations. But this is our process. It's a very long process, and you can see how sophisticated it is, but it takes advantage of exploiting those straight line solutions that we experienced on the phase plane. And of course, different initial conditions are going to produce different results because they may involve both the K1 non-zero and K2 non-zero, but we'd again have to go through and solve for those. So let's just see what would happen if I picked like a solution that was, I don't know, 2, -8, which is somewhere down here. Well, first of all, my constants would be different in here. These guys would be, let's see, 2 and -8. And we'll notice, at least in this case, that our eigenvalues, that our K1 and K2 will not both be 0. So now I would quit and reduce row echelon form again, and now you see that K1 and K2 are both defined. So that would take into account both of the exponential pieces, the e to the 2t and the e to the 3t components. But you know, K1's obviously negative, so we're going to have some negative activity in those zones. So that's our solution process. You know, it is really procedural, but the ideas there are kind of key to making some sense of this. But keep in mind, this is some pretty advanced theory behind this general solution of systems of linear ODEs. And the beauty is it works for more than, you know, ones that are bigger than 2 by 2s. Yeah, but manually computing eigenvalues and eigenvectors, it would be a nightmare, because you were talking third, fourth order polynomials if you're getting into 3 or 4 variables.